because if I forget to record, then no more. All right, finish. So you know. So now it started recording. So maybe tomorrow or on Sunday, then I get it from the cloud. Then I put it inside Canvas. Go to video in Canvas, and you see the whole thing there. All right. Okay. Before we can derive the Kalman filter, we have to do some simple maths. All right. So the first simple maths we need to do is to solve simultaneous equation. And actually, we learn how to solve simultaneous equation in secondary school. So we will solve simultaneous equation in a systematic way, but it's still basically secondary school. All right. So if you have 4 simultaneous equations, so I use the example of 4. Or okay, is like 4 unknown. So here is B1 x1 plus C1 x2 equals to Z1. So x1, x2 are the unknown. The rest are no numbers that are given. All right, then A2 x1 plus B2 x2 plus C2 x3 equals to Z3. Then I have A3 x2 plus B3 x3 plus C3 x4 equals to Z3. All right, then I have A4 x3 plus B4 x4 equals to Z4. So there are 4 simultaneous equations, 4 unknown, x1, x2, x3, x4. This one, secondary school, you know how to solve. Okay, and so here we want to solve them systematically. Now, this can be put into matrix form, so it's obvious. First row is the first row here. Correct? First row is the first row here. Then second row is the second row here. Third row is the third row here. Fourth row is the fourth row here. Okay, so now, and we are also solving a special, this simultaneous equation has a special pattern, is that if you put in a matrix form, you see that this off diagonal are all zeros. Okay, you only have numbers along the main diagonal and the one above and below it. Okay, if you have this pattern, then there is an algorithm called Thomas algorithm that can solve this iteratively. So how we do it? Okay, we write down row 1. Row 1 is this one. Bx1 cx2 equals to z1, which means this row multiplied by this column is equals to z1. So you get this, is this one. Now, then you divide the equation by b1, so x1 become x1, then this one is like that, this one is like that. All right, then we call this gamma. 1. Then we call this row 1. Okay, we do that, then this equation becomes this equation. And then this one, we write it back in the first row, it is like that. Second and third and fourth row, we haven't touched. Okay, so this secondary school haven't do anything, nothing, no sophisticated maths. So we do row 2. Row 2 is like that, so which means you take this, you go and write out this. Then after that, you do the following. Equation 1.2, which is this one, minus a times equation 1.1, which is this one. So you take this minus a times this, you will get this. So this is secondary school again, nothing. You just do that, you'll get this. Then divide throughout by this. So x2 it will become x2 here. Then all x3 is divided by this is divided by this. All right. Then again, to help us write so that you look so complicated, you call this row 2 gamma 2. Okay, if that's the case, then equation 2 is x2 gamma 2 x3 equals to row 2. That I write it here. So this one goes down to here. Then row 3, you take row 3, you write it down. Then after that, you just take equation 1.4, which is row 3 minus a3 times equation 1.3. So equation 1.3 is this. You take this equation minus a3 times this equation. Then you write down, you get this. All right. Then you divide throughout by the coefficient of x3, so you become x3. Then the rest are like that. Okay, then you call this row 3. Gamma 3, row 3. Okay, so repeat. You put back. Then it's the last one. So you take the last equation. Right? Then you take the last equation 1.6 minus the previous equation times times a4. So a4 times this one minus a4 times this, you get this. So again, you divide by the coefficient, you get x4. Then you know, hey, this one is the answer. Correct? Because you solve for x4 already, one of the unknown. So you got the answer for the unknown, x4. All right. So I already show you, you can see the pattern. So in general, you know, no matter you got n equation, n rows, you will know that the pattern is like that. You replace 4 by n. So xn, zn, an, row n minus 1, you know. So you know the pattern and it will be like that. All right. Likewise, all this, you will be gamma n minus 1, cn minus 1. So all this, you will get this pattern. Okay. So, which means given n simultaneous equation, you can solve for xn using this formula. Okay. So now, that is how to solve the simultaneous equation systematically. We will use it in Kalman filter. That's why I need to teach that first. The next thing I need to teach you is again solving simultaneous equation. All right. And it is called least square estimation. Again, simultaneous equation, or if I give you some simultaneous equation, example, I give you, let's say, 2x plus 3y equals to 4. So x and y are the unknown. Then I give you 5x plus 6y equals to 7. Ask you to solve for x and y. No problem, we can solve. Okay, no problem. Nothing to discuss. But if I give you one more equation, then I say, okay. What about we add one more simultaneous equation? 8x plus 9y equals to 10. Then I ask you to solve for x and y. Then you say cannot solve. All right, cannot solve. Means what? If I use the first two equations, solve x and y, then I put inside the third equation sure wrong one. So I didn't solve all three simultaneously. Cannot. I mean, it is quite trivial to say, I can use the second and third equation to solve for x and y. The answer for x and y, I substitute into the first equation, left side will not be equals to right side. So cannot, you know that cannot. So we know from secondary school, why cannot? I say it this way, because if you have the first example I give you was two equation, two unknown, then can solve. I give you three equation, three unknown, can solve. But now I give you two unknown, three equation, two unknown. So this one we say cannot solve. If the number of equation equals to the number of unknown, even I give you four equation, four unknown, you can solve. Five equation, five unknown, you can solve. But here I give you more equations than unknown, so cannot solve. Okay, if we cannot solve, and yet we want to solve, so we try to, so to speak, we try to solve as best as we can, as well as we can. What's the best we can do? Okay, think of the following. So let's say now I got these three equation here. I got these three equation here. All right. Obviously, this three equation is, you can compare with this three equation. Okay, the unknown are theta 1, theta 2. Here is x and y. All the rest are given numbers. So let me just rewrite this three equation this way. I bring all this to this side, then I will get y1 minus phi 1 theta 1 minus phi 1 2 theta 2 equals to 0. Then I rewrite, I get y2 minus theta phi 2 1 theta 1 minus phi 2 2 theta 2 equals to 0. y3 minus phi 3 1 theta 1 minus phi 3 2 theta 2 equals to 0. So what is called solve the equation? Solve the equation means I can find a theta number for theta 1 and a number for theta 2 such that if I substitute here, left side is equals to 0. If I substitute here, left side is equals to 0. If I substitute here, left side is equals to 0. Okay, but I just told you three equation, two unknown, cannot solve. And now I want to solve. So what is the best thing I can do? Since if I substitute here, is equals to 0, that is a perfect solution. All right. But since I cannot get a perfect solution, what I want to do is that after I substitute here and here, I want the left side to be as close to 0 as possible. I substitute inside here and here, the left side to be as close to 0 as possible. The number that I found for theta 1 and theta 2, I substitute inside here, left side is as close to 0 as possible. So I have done my best. All right. Okay. So in layman's words, it's like that. In maths, we will formulate it this way. We will then square this, square this, square this, add the 3 square, and make sure that the 3 square added together are as small as possible. So it's like that. So which means I added the 3 square, the sum I call it V, and I want to make sure V is as small as possible. So you can think of it this way. If I put in some number, since they are all squares, if V is 0.1, then which means this must be less than 0.1. This square must be less than 0.1. This square must be less than 0.1. Because if all add up together is equals to 0.1, then obviously squares are always positive, right? So you add 3 positive number equals to 0.1, then individual positive number must be less than 0.1. So I want to find the smallest V. So secondary school, how do we find the smallest V? We just dV. Last time we always, how to find the smallest y? Dy dx equals to 0. That's what we do. That's standard. So we do the same thing. So take this equation, dv d theta 1. So go and differentiate, equate to 0. Then dv d theta 2, differentiate, equate to 0. All right. If we solve for these two equations, you will find theta 1 and theta 2 that gives you the smallest v. Just like last time in secondary school, you got dy dx equal to 0. Let's solve for x. X will be the value that give you the smallest y, which is the same. All right, so maybe here a little bit more complicated because you got theta 1, theta 2. So last time in secondary school, it's just dy dx. All right, so now it's dy dx1 and dy dx2. It's the same idea. There's nothing more complicated than that. Before I go on, because here you still can write because there are 3 equations only. You may deal with, 1,000 equations or 10,000 equations. So you don't write like that. We will use matrices. So it's obvious that this one, we put it inside a vector. Okay. And call it the y vector. The unknown theta 1 and theta 2 are always inside a vector called theta. And the rest of the coefficient is called phi. So the way for you to do is just check this times this, you will get back the left-hand side. Then this is obviously the right-hand side. All right. So the simultaneous equation will now be written as phi theta equals to y. Then when V is the sum of these 3 squares, you can check. It can be written in the vector and matrix form in this way. So if you use the definition of y, theta, and phi, you substitute inside here, you write it out, you will get back this. Okay, no point going through the detail. You want to go back and multiply, right? Get back there. All right. The secondary school matrix multiplication. Then again, this was secondary school differentiation, dv d theta 1. So you take this, you get this. So here looks so complicated, but you can check if you substitute y, phi theta inside here, you will get back here. Okay, so now you see there's something new. There's a hat here, theta 1 hat and a theta 2 hat. Now, is to differentiate between the theta 1 and theta 2 inside this equation. That hat would be what we call the estimate of theta 1 and theta 2, because it's not going to solve this equation perfectly. It will be the best estimate of theta 1 and theta 2. All right, so that you substitute theta 1 hat inside here, theta 2 hat inside here, theta 1 hat inside here, 2 hat inside here, 1 hat inside here, 2 hat inside here. Then this plus this is as small as possible. All right, theta 1 hat is the best estimate of theta hat 1. Sorry, theta 1 hat is the best estimate of theta 1. All right, in the least square sense, which means you put in, you get the smallest square sum. Okay, just a simple example so that at least you have some numbers to substitute. So, okay, before I go on, so now you get this, then I think this is trivial. To solve this, you now bring this, you will get you bring this over, you will get then after that you multiply left side and right side by the inverse. Okay, so this and this give you I or cancel. Then this one you will get this. Right side. I forgot this. Okay. All right. So for me to, I just call this formula so that later on when I use this, I just say apply the formula. All right. So I just call it formula. Okay. So let's look at one example. So you have here three equation, two unknown, x0 and x1. So this is three equation, two unknown, x0 and x1. So you know cannot solve, right? So how to solve in the least square sense, how to find x0 hat and x1 hat. So you just rewrite the three equation like that. Okay? It's simple, you just put left, put right, you write like that. Then you go and compare the pattern. Oh, this is y, this is y. So you go and compare, then okay, you say, oh, this is y. Okay, so you say this is y. You say this is y. Then the unknown in my formula is always theta hat. So it's always x0 hat and x1 hat. So you look at here, where are the coefficient? Then you decide that phi is equals to, this must be 1 minus 1. So it's 1 minus 1 is 1, 0. So it's 1, 0. So it's 0, 1. So it's 0, 1. All right, if you compare, you will then see that you compare with my formula, you see that now you get this equals to y. All right, you do this, you'll get back this. Then now you go and apply the formula. This formula here. All right, you know what is phi, what is phi, what is y, so you go and find what is theta hat. All right, so this is the formula. I think this is my phi transpose, this is my phi, then this is my phi transpose, this is my y inside the formula. All right, so you do the math, multiply out, you will get this. I think there's a mistake here, so you strike that out. I have to write out properly. So here it should be equals to, so it should be, this one is theta. You don't really have to copy because I will put my slides inside Canvas. Okay, so this would be 1/3, 2/3 would be the number that you put inside here that gives you the closest to 0. All right, that best solve this simultaneous equation. Okay. Now the basic maths part is there already. So now we will start. All right. Begin to apply to the control or signal processing. So now we consider, just as an example, all right, we consider a first order process model. So first order means all the A here are scalar. They are not matrices. C is a scalar, which means A is 1.1 or 7.3, C is 2.1 or 1 or 0.1. It's just scalar. I just want to make it scalar now so that it's easy for you to follow the maths, because later on there's so much math, substitute all the way. In general, A and C are matrices and X are vector, but I don't want to do matrix algebra here. It's the same. Then it's make it even more irritating. I find it very irritating. Okay, so it's scalar. You just follow the derivation with scalar. Then after that, I will just tell you that it's applicable if they are matrices. Okay, so now, and first of all, in Kalman filter literature, the way how to understand all this is X represent what we call the true state. Okay, I will have to slowly explain to you what all this means. All right, this is what the name is called process noise. Okay, Y is called measurement. All right, V is called measurement noise. And R1 and R2 are the variances of the noise. This is the variance of process noise. R2 is the variance of measurement noise. And the noise in Kalman filter is always assumed to be Gaussian independent, zero mean. All right, I will spend some time slowly to tell you exactly what all this means. Let's go through a simple example so that you know physically what this Kalman filter model means. All right, measurement. It really means measurement. So it's like that. Let's give ourselves an example. We know in COVID, we need to, last time when we first started, we need to measure our temperature. You got fever, cannot come to campus. All right. And very often, for practical reason, we will use the gun, point at your forehead. Then we look, okay, 37 got fever, go home. 36, okay. So assuming that the body temperature, normal healthy person is 36. So we will use the gun. So what the gun measure, they see, that would be Y. So if the gun say 37, then 37 is Y. So let's just discuss things like that. Let me find a space to write things. Okay, so let's discuss the process model. All right, since it's called process noise, the true state. And assuming A is 1, C is 1, so life is very easy. So xk1, xk plus 1 equal xk equal plus wk. So I will write the xk plus 1 is equals to xk plus wk. Okay, now, so let's say day 0, k equals to 0. K equals to 0, you're healthy. So your body temperature, which is the real state, is 36. So you're healthy. Now, then what about day 1? Which means k equals to 0, x0, you're 36. Let's say you got fever. So on the first day, at x1, you got 37, which means here you need a plus 1. Okay, now, then this is your true body temperature because Kalman filter say this is true state. Then after that, you go and you think you are sick, so you go and eat medicine. So this is x1 because k equals to 0. K equals to 1. X1 is 37. All right, because this is x, so x1 is 37. So you go and eat medicine, then your temperature, true body temperature, you eat too much, becomes 35. All right, so which means K here, W here is -2. Then after that, K equals to 2. K2, which is this one, is 35. Or this brought over here. All right, at the KX3, you get well, right? You get well. So you become 36. So this must be a plus 1. All right. Now you see, your true body temperature really varies like that. 36, 37, 35, 36. You know that it happens. It's true one. It's your true body temperature. It's really true one. It is inside your body. So in practice, how do you know all this? In practice, we will use, you go and see doctor or what, or at home you use a thermometer and put inside your mouth, measure, then you see. All right, we will say that that is inside your body is true. All right, if you're still not satisfied, you go and measure 1 time, measure 2 times, measure 3 times, take average. So all these 36, 37, 35, that's why it's called true state. All right, it really stick the thing into your body and measure, you are satisfied until you know that it is very accurate. In practice, it is true state or true body temperature. But you know you are like that, but you come to NUS, we cannot stick it inside you, then everybody stick it inside, then the wash, they'll take how long? So they will use the gun, pia, 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 pia. So let's see the gun one. The gun one is the measurement equation. So now we are talking about the measurement equation. So measurement equation is written as YK equals to XK plus VK. So, okay, at K equals to 0, X0 is 36. So I must put 36 here. Then you come to NUS, the secretary go and point, then, maybe it's inside the aircon room, then he measured 35. All right, so he measured 35. That is the measurement Y. So obviously there is a noise term called -1. All right, then at K equals to 1, which is X1. So you see X1 is what? X1 is 37. You actually got fever, 37. All right, he go and use the same thermometer and the same temperature, same aircon room, so he also measure less, so it's 36. All right, then on the 3rd day you come to NUS, they measure you. So here you say, good, go to class. Then on the 3rd day, because you see his thermometer, his temperature sensor gun is lousy, so he got error. So you go to class. All right. So this one, X3 I see here is 35. Actually, 35. There's something wrong with you already. Then this time he didn't measure inside the aircon room. Maybe he go and measure under the hot sun. So his reading is 37. This is +2. So he will say, you are sick, go home, cannot come to class. All right, these are his temperature gun measurement on your forehead. So this V -1, -2 is what we call measurement noise. That is the noise associated with his temperature gun. All right, temperature sensor gun. If you buy a better gun, then maybe this will be not better, maybe not -1, but -0.1, -0.1 plus 0.2. If you buy a cheap one, then it's -1 plus 2. So measurement noise will depend on the instrument you buy, how good it is. Also depend on the environment, everything that is around it when they do the measurement, including the man, how careful he is, how not careful he is, including the sun, the wind, everything. All right, so that will be measurement noise. Here you also can see that, look, here basically says the body temperature by right should be, today should be equals to yesterday. XK plus 1 should be equals to XK. But in reality, we all will fall sick, and then temperature go higher, then normal, then sleep too much, then maybe eat too much of something, then temperature drop more, So even the real body temperature, though we say is equal, but it's not really equal. So you also need to have another Gaussian noise here to model the true temperature in your body. Okay, so this is how these two equation, the interpretation of these two equation. Okay, now it is 6:50. Go for 15 minutes break. Go and drink coffee. Go toilet. Come back at 7:05. I start again at 7:05. Okay, let us start. All right. Okay, give you a 1 minute revision of this statistic. R2 are random variable, Gaussian independent, zero mean random variable with variance R, R1 and R2. So what does that mean? Okay, actually you learned before in maths, but I just quickly go through with a very simple example so that you to make sure you know. So in this case, V would be here is -1, -2, -1, 2. So if you measure one whole year, you will 365 days, should be, -1, -2, it won't be integer, maybe then you got a plus 1.5, plus 0.5, minus 0.1, minus 0.9, all sorts of numbers. All right. But so we model this as a Gaussian independent variable with zero mean. So let's take these three numbers. So if you look at these three numbers, I need to find a place. All right. So you draw the noise V, you will draw it like that. So when you have k equals to 0, your V is -1. So you got a noise at -1. When k is equals to 1, your V is also -1. So you have this here. When k is equals to 2, your noise is at 2. So you have 2 here. All right. In this simple example, you see it is 0 mean. All right. -1, -1, 2 is average is 0. Mean is the same as average. All right. So you get 0 mean. Then there is this term called, now it is like, because random variable, you sometimes big, sometimes small, sometimes positive, sometimes negative. So people want to know, hey, how big is a random variable? So you say 2 is also wrong, you say -1 is also wrong. So you tell them the standard deviation is 1.4. Then that gives you a sense of the magnitude of your random variable. So if you tell them 1.4, so they know it varies between, 0 means standard deviation 1.4. So they know it fluctuates. The average magnitude is about 1.4. Maybe you get 1.7, you get 2, sometimes you get 3, sometimes you get 0.1 or -0.7. But on the average throughout is 1.4. So standard deviation gives you an idea of standard, amplitude, standard deviation. So you don't expect, if I tell you standard deviation is 1.4, you don't expect your noise to be 20, 30. Oh no, standard deviation 1.4, how you get 30? And in theory, you can, all right? But that would not, the average number is 1.4, all right? So then in practice, you think, well, maybe it vary up to 3, maybe seldom 4, 5 would be very rare already. You get 20, maybe 1 in a million chance, that kind. All right, so give you a sense of what is it. So first of all, so how you go and get the variance and the standard deviation? All right, first of all, we calculate the variance. So variance is calculated like that. This is the formula that we will use. You will take this. So this is what? The first one is -1, so it's -1. You have to subtract away from the mean. In this case, is 0. You square it. The second number is what? Is -1. You have to subtract the mean. Then you square it. The third number is what? Is 2. You have to subtract the mean, and then you square it. Then you divide. All right, since there are 3 of them, you divide by 3. So you get a number I calculated, which is 2. So the variance is 2. The standard deviation is always like that. All this has been taught to you in statistics, but a quick revision. We just do a square root of the variance. So in this case, it will be 1.4. So you see 1.4, if you draw a line here, 1.4 is here. So this magnitude is 2, this magnitude is 1. So 1.4 is the average of the 3 number, that kind of thing, magnitude. Of course, these are statistics. You don't use 3 numbers. It is meant to use hundreds and thousands of numbers. All right. So R1 and R2 would be the variance calculated like that, which means you take a Gaussian independent random variable with standard deviation of 1.4, you can generate 10,000 numbers. It will fluctuate like that. Maybe I draw for you. I will expect it to fluctuate like that. So this is K. This is VK. So I will expect it to fluctuate like that. Okay, and then if you do a 1.4, you will say that, yeah. You know, 1.4, you know, some are bigger than 1.4, some are smaller than 1.4. So it's true for here also. So it's 1.4. So some must be bigger than 1.4, some smaller than 1.4, that kind of thing. So minus 1.4. But 1.4 will give you a good idea of the magnitude of your fluctuation. All right, so I only require you to know, this is really knowing what is the meaning. It's not just maths, know how to calculate, without understanding what it means. All right, so standard deviation really means this. So let me write down. So standard deviation means this. All right, it means this. When you do a MATLAB, you go and calculate, you will get something like that. Some more than 1.4, some less than 1.4, like that. Okay. Now, let's then go and see how we solve for this model. Now, I must say first, from now to the end of tonight is maths, and you should focus on just follow the maths. And it's simple maths, very simple, all secondary school. All right. Tonight, I will not give the interpretation, the implication, which means I will not explain the why, I will just explain the what, just do maths, just substitute here, substitute there, get the simultaneous equation solved, get the maths solved. Next lecture, then we'll begin to interpret, what does this mean? What does that mean? So your job tonight, don't worry too much. You don't understand what's the implication of this and how to interpret that. All right. You just make sure you can follow the steps, and they're all secondary school. Mathematics, simultaneous equation, nothing. Okay. So now I show you we do k equals to 1, 2, 3. I'll just show you we do k equals to 0, 1, 2. Of course, in practice, in control or in signal processing, your sampling could be 1 second. So, after one minute only, you have 60 sample. 2 minutes, you have 120. So you have hundreds and thousands of all this number. So let's now look at these two equations, like what I've done here. All right, I write it down here. So which means I consider all the way up to k equal to 5. So I just write, okay, x1 equals to ax0 plus w0, so it's here. Then y0 equals cx0, v0 is here. Then x2 equals to ax1 plus w2, so plus, yeah, w1 is equals to here. So I just write all the way up to k equals to 3. So these two equations, I just write all the way here. Now, Kalman filter, we want to estimate the true state, which means these are the true state. In my example, what is the temperature of inside your body on day 0, x0? What is it? What is the true temperature inside the body on day 1? What is the true temperature inside your body at day 2? Inside your body, what is the true temperature at day 3? Of course, you have measurement. You take the gun, just shoot you. We won't use thermometer and stick inside your mouth. It's not practical. So which means given all the y and a and c, all right, we want to then find x hat 0, x hat 1, x hat 2, x hat 3. All right. I say again, measurement will be taken. So y will be a known number. So in my example, you don't know this side. We are not going to, it's not practical to, use thermometer stick inside you, for there are many applications that it's not practical to go and to go and do a lot of work to find the true state. From there, we want to estimate the true state. So from the measurement, we just use a sensor measure. Sometimes there are certain things in application, engineering application, you can't even reach it. All right, in semiconductor, the wafer goes through all the machine. Contamination, you cannot even use the sensor to go and measure the temperature of the wafer. You can't even touch it. All right. So but you need to know the temperature of the wafer. So it's very, in many engineering application, you have to, based on your measurement, try to estimate the true state, which means the true temperature of your wafer. All right, it is common enough. So now we have this. So the first thing is clear now. What we have, the problem is, you count, is 7 equation, 4 unknown. Unknown is x0, x1, x2, x3. 7 equations sitting in front of you. The first thing is we assume that all the noise are 0 first. Okay, we just assume that the noise are 0 first. If that is the case, then you rewrite this equation. It becomes like that. All right. And then you all bring it to the left side, then right side equals to 0, and then you square it, then you get this. Okay, which means you just basically bring this to the left side, so it's x1 minus ax, so equals to 0. So this is a minus sign, is equals to 0, is a minus sign, is equals to 0, it's a minus sign, is equals to 0, it's a minus sign, is equals to 0. All right, there as before, I square this all the way, this, I add up all the squares, so it is here. All right. Then to find the x hat 0, x hat 1, x hat 2, I make sure I find the smallest j. The smallest j, when then will give me x hat 0, x hat 1, such that when I substitute inside here, the left side is as close to 0 as possible. It's as small as possible. Right, then now we take into consideration the noise, which means now all these are not 0. In Kalman filter, we work like that. So W got a variance of R1. V got a variance of R2. So it's like that. If you look at these two equations, as far as maths is concerned, this is one equation, this is another equation. If, example, if W has a variance of 1 and V has a variance of 2, then we know that this equation 2 has more noise, bigger noise. All right, this equation 1 has less noise, less random variable, less noise, as in the random variable here is smaller. Then we will trust equation 1 more. If we trust equation 1 more than equation 2, so the way we will do is all the equation 2, we will divide by R2. All the equation 1 will divide by R1. Because equation 2, R2 is 2, R1 is 1. Actually, the equation 2, the importance of the weightage is actually half of the equation 1. You see here. So now I wrote it like that. Then I rewrite like that. All the x equation, you see, I divide by R1. All the y equation are divided by R2. So if R2 is 2, R1 is 1, then this second half has less contribution to J. And so the y equation or the measurement that you get has less influence in finding your x hat. All right. And in a sense, it's proportional, which means if this is 2 times more than this, then this is half of this. If this R1 is 2 and R2 is 10, and you divide like that, you find that this is 1/5 the weightage of this. It is easy to see. It is easy to see, as far as maths is concerned, if one of them is infinity. All right, which means, let's say your temperature sensor is spoiled. So basically the noise you measure in it is all over the place. So the R2 is infinity. So what will happen? As far as the solution is concerned, you will be, this R2 is infinity, this will be taken out from the J equation we call objective function. So which means this part don't exist if R2 is infinity, which is correct. You use a spoiled sensor. That's why the variance is infinity. All right. So don't consider them. So that's why you can see straight away this type of weightage makes sense in practice. Okay. Now, so of course in practice there's a weightage, there's a ratio between the two, and depends on which one is more accurate, how good is your sensor and so on. All right, so now J is written like that. After taking into account W and V, the variance. So like I said before, then you want to find the smallest V. No, sorry, smallest J. So standard is standard. Differentiate J with respect to all the X0, X1, X2, X3. So you just go and take this, do secondary school differentiation, you will get this. And then equate it to 0, 0, 0. All right. Then work hard a bit, write this in matrix form when you got it like that. All right. This 4 equation written in matrix form looks like that. Then you see already, then you say, oh, okay, that's why I teach you Thomas algorithm. You see? Look, here diagonal all 0. Same pattern. All right. Then you see here and here is the same. I call it alpha so that, it's not so difficult. So all these are alpha, alpha, alpha. All right. And then you see this and this. I call it beta. I call it beta. All right. This is alpha. Then you go back and see, hey, this and Thomas algorithm, same pattern. So same formula, same solution. See, same pattern. All right, it's 0 here, 0 here. Then you got diagonal and the diagonal above and the diagonal below. All right. So all your x1 to xn is here. All right. All this z, obviously that I call y. No big deal. So then you just match. The solution for xn is like that. So it's Zn minus A rho n minus 1. So you go and match Zn. So you go and match. Basically nothing, you just go and use the formula and apply the formula. You just apply the formula. Okay, so from here, all right, is because here is just 4 equation. So of course, in general, you will get like that k equation. All right, so you can match. So then your xk, you go back and look. Your xk, you use this formula xn. No? Okay, then row n minus 1 will be this, and this one, gamma n minus 1 is this one. So you go and match. Match the formula, you will then get xk equals to this. You go back and match, nothing, no big deal, just match, you will get that. Okay, nothing to explain except just monkey see, monkey do, here, all correct. Okay, then in Kalman filter, they call this P. It has meaning, P has meaning, I will discuss next week. So as far as maths is concerned, this is called P. So it's P, where P is that. All right, so that's it. So you got your xk. I say again, this formula, you go and match with the Thomas algorithm formula, then you get this. Because this pattern is the same. Then you do the same, this is xk, you want to get k minus 1, so it's very simple. Where every time you see a k, you replace it with k minus 1. Here you replace with k minus 1, k minus 1, k minus 1. Then you get the same formula for x at k minus 1. So it's like that. So everything you see in 20, 21, 22, 23, everything here, you see k only, you replace by k minus 1, you will get this. So this is just maths, nothing. Whether it's so now what we want now is to use 20, 21, 22, 23, which is solution for k, xk, and 24, 25, 26, 27, which is solution for xk minus 1, to do secondary school algebra, very tedious, eliminate variables, substitute here, substitute there, substitute until I also get headache, so that finally xk is in terms of xk minus 1. Okay, so in a way there's nothing to teach, there's nothing to learn here except you just substitute here, substitute there, so that xk in this equation and is connected to xk minus 1 in this equation. Basically, that's all there is to it. Okay, I say this is because why you want to do this, so that we get a recursive algorithm, so that when after calculating xk minus 1, we can use that to calculate what is xk. You will see more, you'll become clearer when you do the tutorial question and next week when more applications are there. But like I say today, don't worry about the implication. Just make sure you can follow the maths. That's it. So okay, now I will start to do the recursion, which means the tedious substitution here, substitution there. If you can't follow, never mind, because there is nothing. You go home, you concentrate, you can find out already, because it's secondary school maths. Okay, equation 24, you can write it down like that. So if you work hard, you go and look at 24, which is like that. You put something on the left, something on the right, you'll be right, you will sure get this. Then you take equation 24 and substitute into 23. So 23 is this one. So you write down 23, rho k minus 1. If you substitute that into this, you will get this. All right. Then after that, you see, this is the same as this, which means this in equation 23 must have been substituted, got rid of this. That's why this appear here. All right, I'm just going to see. All right, so again, in equation 23, you must have this z minus alpha rho. 23 is z minus alpha rho. So this one must have been replaced by this. That's why it's here. All right, this is actually equation 24. Originally, this part is z minus alpha rho. Okay, so now it's replaced by this. Nothing. Then you go and look at 25. From 25, you can sure write down this one. Then you go and take this, substitute into 28. Then 28 will look like that. All right. Again, you to help you, you look because look until you are blurred, then you can see, hey, this one and this one is the same. Okay, which means in 28 there must be this term there. Then this term is now replaced by this one, that's why it appear here. All right, just go and see. Then take this, they say substitute into equation 20. So substitute into equation 20, then you get this. All right, then you look at 20. 20 must then contain this because I see this. And this is the same. So 20, this one must have been this. Okay, secondary school. Sometimes I also read until I find so confusing to follow. All right, then take this equation, add and subtract axk minus 1, which means you add axk minus 1 here, then you subtract axk minus 1. So the right hand side, you add and subtract. So which means you have not done anything to the equation. It's still whole. Okay. All right. You see this one, add and subtract. This means this is added here. And this is subtracted here. Okay. There's a p minus 1 here because there's a p here. So if you multiply, it's gone. So you really add and subtract axk minus 1. Then go and look from equation 21, you can write like that. Then you go and look at equation 21, I guarantee you will just rewrite this form. Then go and substitute this from 22 into here. So this one become like that. So I think without looking back here is the same. This is the same, this is the same, this is the same. This is changed. So if you look, this must have been replaced. This. Yeah. This must have been replaced from 22 by this. All right. Then after that, substitute this from 25. So what did 25 do? PK is the same, beta is the same, a squared over r1 is the same, minus alpha is the same. So 25, what they must have done is this one must have been replaced by this. All right. Okay. Then substitute into 29. So take this, put inside 29. So this is what? PK minus 1. So 29 is the XK equation. So XK equation. So since they say this substitute into there, I think this thing looks the same as this. Okay. So I think previously this must have been PK minus 1. All right. Then you rewrite, you will get this. You rewrite this equation, you will get this. So I should say here, rewriting, you will get this. Now, then here I tell you, if you work very hard, square bracket is equals to 1. You see the square bracket is here. If you want, you go and, do our inverse. Because to make life easy, just think of all this as scalar. All right, inverse means divide, inverse means 1 over p. So you do, you will find that at the end, the square bracket here is 1. So 1 multiplied by this is, you don't see it, so you just left with this. And then left with this. So basically 1 disappear. 1 times something is that something. So x hat will look like that. Then after that, here is z. So get z from 19. So z now 19, it becomes y. So 19 will change z to y. So z becomes here. All right. So now you can see that the solution for xk is written in terms of the solution from xk minus 1. All right, xk minus 1. So which means if you know what is xk minus 1, you can calculate what is xk. And then, of course, if you know what is xk, when k increase, every time the new xk is calculated from the previous xk, which means the new x hat is calculated from the previous x hat. So you get the iterative algorithm. All right. Now, this in Kalman filter literature, the notation is like that. They make a distinction between xk that is estimated using yk. So they call this, let me write this properly, in Kalman filter, they write this x hat k stroke estimated using measurement at yk. This one is the x previous estimate at k minus 1 estimated from the measurement at yk minus 1. Okay. So if I see a k here, I know that your x hat is calculated using yk. The first k is the sample of x. If I see a k minus 1 here, I know that x hat is estimated or calculated from yk minus 1. You will see later on why I say that. So, which means if you use command filter notation, this equation now will be written like that. This will now be written like that. This will now be written like that. And this will now be written like that. Why do we need to write that? Because we can calculate xk from y measurement at k minus 1. Now, I say again, this is x hat calculated from yk. I can actually get x hat calculated from or estimated from yk minus 1, which is this one. In command filter, we do that. That's why we need to make a distinction. This number and this number is different. So if k is day 3, yeah, it will be x33. This will be x32, which means this is my estimate of your temperature on day 3 using the temperature that we sense on day 3. This is the estimate of your temperature on day 3 using yesterday's temperature. I haven't measured you today yet. How are we able to do that? Because equation 13, you go back and look at equation 13. Equation 13 is like that. And W is supposed to be a zero mean. Zero mean means on the average, the noise is 0. So if I ask you what you think is your temperature today, you have the temperature yesterday. And on the average, the noise is 0. So I will just take, if A is 1, then I just take today's temperature is the same as yesterday's temperature. If A is 0.5, then today's temperature is half of yesterday's temperature. So it just depends on the model. All right, because this is zero mean. So this is an educated guess. After all, the noise is, that's how should I say? It's the best guess. You just assume noise is 0. All right. And the model is such that it is zero mean. All right. So on the average, you are correct, that kind of thing. So, but remember what I say? This is estimated from this, assuming that this is 0. Did I involve the measurement in estimating this? No, I never. Okay, never. If I involve y in estimating this, then yes, it will be y. It will be xk plus 1 slash k plus 1 or xk slash k. But if I never use yesterday's temperature, today I lazy, I don't take. So it will be xk slash k minus 1. All right, so you see where was I? Yeah. So xk minus 1 is equals to, if A is 1, then I just take yesterday's temperature, assuming that your noise is, your body temperature today is the same as yesterday, which makes sense because we know we hardly change unless you are sick or do some funny thing, go for marathon or something like that, or whatever, you go and play or go and sleep the whole day. If not, it's an educated guess. All right. And this guess was based on yesterday's measurement. Today I didn't take Y measurement into consideration. Whereas this, you see Y appear here. To calculate this, I have to make use of Y. So there is a difference. Okay. Then, so then you rewrite, they say rewrite 33. So rewrite 33, you get this. All right, because this is the same as this. So this can be replaced by this, so it comes here. All right, so you can be just the maths you can rewrite. And then 36 is 36 is basically saying what? This estimate depends on the previous estimate. So this estimate depends on the previous. If this k minus 1, if this k plus 1, so this k. It just mathematically, it just means that. All right. You just take the last estimate to get the xk minus 1. So you just take if you want to xk plus 1, you just take the last estimate and then do the k plus 1. So this equation and this equation are basically the same equation. All right. It's just the current and previous. So what is current, what is previous? You just bring. So now they say equation. So finally 37 into 38. So basically you put 37 inside here, you will get this. So now you see, you get this estimate, a function of the previous estimate plus this. All right, so this is all up to now is just equation, all maths. Okay. You can see the current estimate is obtained from the previous estimate. So there is one more. We need to find out what is P and to find the recursion for P, okay, which we will do now. So we now need to find P and obtain from Pk minus 1 is again recursion. Okay, so now you take 17, 18 and put into 31, you will get this. All right, what is 31? 31 is this P minus 1 equation. So 17 and 18, you go and put inside here, you will get this. Okay. Then you go and do some maths, you will get this. And again, this one is the P that involve the Kalman filter. The way we write is this one. This is the P that involve YK. Because there will be a P that involve only YK minus 1, doesn't involve YK. So that's why we need to make a distinction. Okay. Then you go and look at 41. You will then get this. Now, the meaning of this, I will use example 4 to explain. All right. Basically, this one, as far as maths is concerned, we are calling this pk minus 1. Okay. So you just have to accept that this is defined as pk minus 1. So now you substitute 42 into 41, you will then get this. Then you do a bit of maths, you will get this. All right. So again, the relationship here is k and k minus 1. I would like to get a relationship between k plus 1. So you just replace k by k plus 1. So 42, you just replace by k plus 1, you will get this. Then substitute from 44 inside here, you will get this. All right. Don't worry if there's nothing, you just go back and do substitute here, substitute there until you get that equation. So finally, 34, 40, 43, you will get this. And then you do some more substitution, you will get this. There's nothing more, to say. Okay, what I need to say now is this. Because last time when I first teach, I write in matrix, I find that it's so very hard to go through in the lecture. So that's why I write things down in I say it's scalar, so you can divide. If last time matrix, you cannot divide, you have to do an inverse. And then the order also, you must be careful. Matrix multiplication, A times B is not the same as B times A. So the students see until even unnecessary confusion. So I say, treat all this as scalar. All right. In practice, all the ABC can be matrices. Okay. If you like, you rederive everything. You don't go and divide. Every time you see a divide, you go and do an inverse. So we all know matrix algebra. You will see A, B is equals to C, D. Then you want to find A. For me here, it's very easy. I just put CD over B. But if you want, too bad. If you want, you will have to do A, B inverse is equals to CD, B inverse. All right, then you can get your A equals to CD, B inverse. This is the matrix equivalent of this. Okay, and then you have to be careful. This B inverse, is it in front or behind? And then that kind of thing. All right, an extra layer of. Obviously, if you want to find B, to me, I will just write CD over A. But if you want to find B, no, it's not so easy. You have to do an A inverse, A here, B. So on the right side, you do an A inverse CD. Then this one, you get a B, then you get a A inverse CD. Okay, so sometimes to me, it's just divide. Sometimes you got to invert is behind, then invert in front. Okay. So in practice, all the A, B, C, P can be matrix or vector, all right, like that. You will get the same answer. So now the Kalman filter, I summarize it for you. The model is like that. We see before where W and V are zero mean independent Gaussian variable with covariance matrix. R and R1 and R2 are matrix also. All right. In scalar, it was easier to explain. Then now it will be matrix. Then you will see in tutorial matrix what it means. The Kalman filter is given in many books. It is given in this equation here. 1, 2, 3, 4, 5, 6 equations. All right, these 6 equations, all right, which is 52, 53, 54, 55, 56, 57, is collected from 47, 48, 37, 39, 44, 49 in the scalar case, which means you go back and look at 47, it is 52. You go and look at 48, it is 53. Okay, I just collect here all together, and this is what people call the Kalman filter. Okay, so all the 47, 48, 30 were the derivations. And you see that all this now has been derived for the scalar case. So as far as we are concerned, A, you use it as a matrix. So it's the same. Okay, I mean, if you want, you go home and re-derive using matrices, you end up with this also. The logic, everything is the same. The maths is the same, except you have to deal with matrix algebra, which I want to avoid. I can't explain it. I mean, you make my explanation even more confusing in class. Okay. I think I will stop here tonight. I think it's enough. Okay. I see you next week at the same time, and we'll continue. Okay, so tonight is just maths, and we have reached here. Okay, I'll stop here.